let's continue.
Start it.
Yeah, we're getting started. It's just end whenever.
We got 5 minutes. It's gonna be famous.
Let's go.
Okay, so we have Michael Falk, who's a professor of material science and engineering here at Johns Hopkins University. He's an expert in molecular dynamics and hard-based simulations of these hard materials. And today,
Yeah, see, did you have a pointer?
yeah,
I do.
actually,
Yes, yeah.
Okay. And thanks for organizing all of this. So I'm going to talk a little bit about atomistic simulation. And I wanted to, I mean, I know it's mostly a student audience and many people who may be starting or thinking about computer simulation in the early stages of your career. So I wanted to start where I start when I teach my advanced molecular simulation course. So I like to bring this small piece of text, which is a 1 paragraph. I'm going to just. It's a 1 paragraph story that seems to be a piece of text from a manuscript written in the 17th century, but in fact was written by Jorge Luis Borges, an Argentinian writer in 1946. And it's called On Exactitude in Science. And the story is that in that empire, the art of cartography achieved such perfection that the map of a single province occupied the entirety of a city, and the map of the empire the entirety of a province. In the time, those unconscionable maps no longer satisfied, and the cartographers' guild struck a map of the empire whose size was that of the empire, which coincided point for point with it. The following generations, who were not so fond of the study of cartography as their forebears had been, saw that vast a map was useless. And not without some pitilessness was it then that they delivered it up to the inclemencies of the sun and winters. In deserts of the West, still today, there are tattered ruins of the map, inhabited by animals and beggars. In all the land, there is no other relic of the disciplines of geography. So my question to you is, why would I bring you this piece of text to talk about simulations? Simulations are maps of things. Yes, in a sense, when we make a simulation, like a map, it's a representation of another thing, right? And so other things connected to this text that relate to that? Yes.
I mean, the more precise things, longer text, less.
Right, so often you can imagine in your mind, I mean, I think like with any endeavor, you have to imagine in your mind, what is it I'm trying to achieve here? And I think with simulations, there is a tendency to think, well, I'm trying to make something that's as good and precise a map of the thing I'm trying to represent as the thing itself, right? But the problem is with simulations, as you try to make something more and more precise, invariably you run into these problems of, it takes so long to run. I'm never going to get to the end of this simulation, right? And in a sense, a map of the world that was the size of the world would be useless, right? So the essence, what's good about simulations is that they're not exact representations of what you're looking at. It's that they're simplified representations. And so, I think one of the things I think my take-home message for you for this talk is that imperfect models can provide profound insights. And in fact, all models are imperfect models, right? So we can seek to include more and more detail in a model of a system as we're trying to simulate it. But in terms of our ability to then get useful information from that simulation, we may be doing ourselves a disservice. And this comes up in the timescales for molecular dynamics simulations. The more intricate the model, the longer it takes to run, the less time we can look at. It comes up in our ability to explore phase spaces in Monte Carlo simulations, and that rather than focusing on exactitude and brute force applications, we need to think about simulation as itself a creative endeavor. And in particular, what I hope to do is share with you just 2 examples from my own work and work of a couple of people who are here, Spencer Fajardo and Vicente Munizaga, who will be helping to run the afternoon sessions. And just to show how, what does simulation allow us to do? Sometimes it allows us to explore materials physics in a way that just, we can't even conceive of how we would do it in a laboratory. And sometimes it allows us to leverage statistical physics in a way that allows us to understand complex kinetic processes that would be very difficult to quantify experimentally or understand. So I'm going to start by talking about metallic glass. So maybe not everybody here is familiar with glass from a material standpoint, but it turns out, many of the materials we interact with on the day-to-day, all metals or most metals we interact with, many polymers also are crystals, right? And we often start the discussion of material science from the standpoint of crystals. But almost any kind of material can also be made in an amorphous structure. And those amorphous structures we often refer to as glasses. And that includes well, the most common glass we interact with is, of course, the window glass, silicate glasses. But also silica is an important glass. These kinds of silicon-based glasses are used extensively in solar panels. Also, many plastics are formed in an amorphous structure. Dental prosthetics. But I'm going to talk today about metallic glasses because although it's difficult to turn metals into glasses, you can do it, and there are some interesting reasons why you might want to. One of them is that they can be stronger than crystalline metals in certain cases. Another is that they can be formed in different ways than crystal materials, that they don't have to be cast in a process during which they undergo a discontinuous phase transition and shrink. And I'll show you a video about that in a minute. Another is we're currently working on some research to understand how they might be useful for additive manufacturing. We're using laser processing and cooling metals very quickly, which can lead to glassification. So what I wanted to do is show you this video, which is my favorite video of all time in terms of making material science sexy. So it's for a watch festival. Oops.
This bezel is an aesthetic wonder, a technical marvel, an unlikely composition of two dramatically contrasting materials, a zirconium-based alloy called liquid metal and ceramics. We start by forming a host of ceramic rings, which we subject to incredible punishment. They are heated in an oven to over 1400 degrees Celsius, resulting in a ceramic which is so hard that it takes an 8,000 watt laser ray to cut cavities into the surface of the material. But it's only after heat flattening the liquid metal alloy under a concentrated pressure of 5 tons that the special alchemy can be performed. The heated liquid metal is pressed into the cavities in the ceramic material. The result is a bezel which will retain its striking appearance indefinitely, thanks to the hardness of the two seamlessly bonded materials. The liquid metal numbers and scaling will appear in bold, vivid contrast to the glossy ceramic background. Forever.
Wow. So the technically interesting part of that video is that, the thing that having an amorphous alloy lets you do is that you can have a solid metal that you can heat up to a high into this glass transition region where you can push it in, where they push it into the ceramic surroundings. So you can do this sort of near net shape forming. But I think, yeah, I don't know, whoever put that together, it's kind of very inappropriate.
Why does it sound like the cadence of it reminds me of like a fan fiction?
It's, yeah, absolutely. It's like a fan fiction for metallurgy. What is it about these amorphous metals that make them interesting to me? It's that they have this disordered structure, right? There's no crystal structure there. And so many of the concepts that we use to think about why crystal material undergoes plastic deformation just don't apply in these cases. So let's think about how do we understand how crystals react when they're exposed to very high stresses. So this is a simulation that was done back in 2002 by Farida Abraham and company. And it's a simulation of crystalline copper. Most of the atoms you're not seeing, they've been removed from the visualization because this gives you a sort of X-ray view into the copper crystal. And there's a little cracked tip at the top and the bottom. And now they're going to start pulling on it. And what we'll see are the atoms that are not in perfect registry with the surrounding crystal. And so what you see is this like explosion of spaghetti-like stuff that starts coming out of the two crack tips and then forms this very disordered region in the crystal that's comprised of many, many interlocking dislocations. And these dislocations are each line-like defects that occur in the crystal. And most of the things we know about how plasticity happens in a crystal come from the fact that we understand a lot of things about dislocations, how they move, how much stress it takes to make them move, how they interact with each other. And a lot of the engineering that goes on in crystals involves changing things related to how dislocations are interacting with their surrounding medium and each other. But what about amorphous materials? Well, amorphous materials are quite a bit more complicated. If you look at them, you don't see any crystal structure. It's hard to imagine. I mean, there's no conceivable way in which you could get a dislocation to move through such a structure in an even way, the way they do in a crystal. So what we've been undertaking are the kinds of things you can only do in a simulation. And by that, I mean, we create a model of this amorphous material. And then we're able to use the computer simulation to grab some region of this glassy material and subject it to shear, because we know it's shear that causes atoms to rearrange or materials to rearrange. And so what I'm depicting here is just that we freeze some number of atoms here. We call them these constrained atoms. And then we have some atoms that are able to be free. And we constrain the atoms in the yellow ring to shear. And then we minimize the energy of the atoms in the center subject to that constraint. And in that way, we're able to impose a shear stress up until the material undergoes some kind of discontinuous failure and record how much stress did it take to get that failure to occur. So what this might look like is something like this. So here you see a sort of random collection of atoms. Here, this is sort of a binary alloy. And then you see there's some little region here where things are starting to undergo a kind of failure point, a rearrangement, and we just record the stress it took to make that happen. So having done that, what we can do is we can imagine doing that at every point in this block of material. And here we've just colored the local region by how easy it was, here red being easy, to get the material to undergo some kind of discontinuous rearrangement. And then what we can do is grab the entire block of material from the boundary and see where does it end up rearranging when it's not probed locally, but it's probed at the boundary. And these numbers, 1 through 10, are showing the 10 first locations where that material undergoes rearrangement. So by probing the material locally, we're able to get some information about its susceptibility to rearrangement that helps us understand the global properties. And I think, this is the kind of thing that you can imagine doing in a computer that would be very hard to replicate directly in an experiment. So what insights do we get from doing that? So this is showing a block of material. Again, here the reddish green parts are the ones that have low stresses to rearrangement. And of course, if we shear, we can imagine shearing in many different directions. So the parallelogram in the middle is showing the direction of shear that we imposed on all of those local rearrangements. And then the color is cycling through the stresses that were required to create rearrangement in that particular orientation. And so what you can see with your eye from a visualization like this is that regions that were quite weak in one particular direction of shear are quite strong in another direction of shear. So it immediately points out that there are aspects of the material microstructure that are highly anisotropic in their response to shear, right? And so this is just an example of the kinds of insights we can obtain by doing these kinds of probings that are really possible in the computer that might be very difficult to do in the lab. So I'm going to take a little segue again and talk about Hilda Geringer, because in working on this work, I decided, well, I should really read some of the past literature about the mechanics of plasticity and how we understand that in metals. And a lot of that work was done in the middle of the 20th century, early to middle of the 20th century. And in reading the history of that, you don't come across that many names of women who were working in plastic deformation theory of the time. Right? So this name Hilda Geringer came up, and I wanted to know more. So I'm going to tell you a little bit about Hilda Geringer as a slide. So she was a significant contributor to plasticity theory. She was born in 1893 in Vienna. She was actually only the second woman to receive habilitation, that is permission to teach at the college level, in mathematics in Germany. But in 1933, her promotion was put on hold because of the Nazi civil service laws precluding Jews from university teaching. She then, as a single parent, she fled with her 11-year-old daughter to Turkey, where she worked for some time. And she developed groundbreaking work on slipline theory, associative principles, the yield surface, the statistics of genetics, many other topics. And then in 1938, she managed to emigrate to the United States and worked at Bryn Mawr and Wheaton colleges for the rest of her career. So, I mean, again, maybe following on Eric's story today about 21-year-old who revolutionizes a field, I think, we have to think that many of the people who come before us have struggled mightily to do the things that provide the background for our own work. So what was the work that Hilda Geringer contributed to? So it was the concept of the yield surface. Basically, the idea that you can think about a space of stress, and these are the principal components of the stress, here described in 3 dimensions. And then if you think about that, if you move along the 1-1-1 axis, that corresponds to pressure or compression or hydrostatic tension, that in general in metals, you don't see plasticity under pressure or hydrostatic tension. But if you move in other directions, you reach a surface, which you can describe as the stresses within which you can stay elastic, but when you hit that boundary, you start deforming the material and behaving plastic. So if you take a slice through this, you can think about the yield surface in a 2-dimensional projection as this sort of oval shape. So this is a figure from the 1924 paper by Mises. So, and this has been confirmed in materials like glasses, even though they behave very differently at the atomistic level, they actually behave very similarly macroscopically. So this is a sort of mapping of the yield surface for a metallic glass that was done by Chris Hsu and Alan Lund. And you can see the shape is very similar to the textbook from 1924. So what we're interested in is how does this sort of macroscopic behavior that mirrors the same things we see in crystals that behave through dislocation deformation, how does that arise from the microscopics of the glass? So what Spencer's been working on is understanding what is the local yield surface. So if we think about this yield surface concept, which applies at the macro scale, what happens when we reduce down the length scale and we're thinking about small regions of the glass? Do we see a yield surface? What is the shape of that yield surface and what does it correspond to? Can we see reflections of the microscopics in the yield surface? And so here you see, this is the yield surface, so this is the yield stress as a function of the angle. So we decided not to plot it in a polar way, but to plot it just on an XY grid or yield stress theta grid. And you can see it has some very interesting features. And it turns out, just looking at these, we can suspect that these are kind of the kinds of features we would expect if we had local weak slip planes embedded in the material. And that we can imagine what the shape of that might look like, and the shape seems to correspond fairly similarly to what we might expect from local weak regions. And so what Spencer's been doing, and I'll show this quickly in a minute, is sort of stepping along this angle and trying to correspond areas of this local yield surface to different deformations that happen in the probe region. And so I'll start this in a minute. So what you'll see is, as we scan through the yield surface, we see different regions of the material undergoing deformation. And particularly if we stay in one particular region of the yield surface, so let's say we stay over here, we see things seem pretty similar. But if I now transition to a new well, we see things are quite different than they were in the prior well, right? So we can sort of relate aspects of the structure to aspects of the yield surface. So this is a sort of summary of what we've been doing in that respect, that we think, computer simulations give us an opportunity to look at these objects like the local yield surface, to use them to get an insight into how the microscopics of the material result in their macroscopic properties, and provide a sort of window in to the material that we can use to develop theories about how these materials respond. So I want to be mindful of time, so I was going to talk about a second example.
2 minutes.
Okay, so I'll quickly talk about a second example, and this is work on understanding the kinetic processes that contribute to the strengthening of lightweight alloys. So this is clearly an important topic, right? We're in a point where we need to be thinking very carefully about efficient uses of energy. And so being able to transition to lightweight alloys for things like transportation is clearly a priority. So how do you take a metal such as magnesium, which is very lightweight but very brittle, and turn it into a metal that can withstand high stresses and not fail through brittle failure? And so the typical way we do that is by alloying, adding other impurities to that metal in ways that will change its microstructure by creating sometimes secondary crystal structures that will interfere with that dislocation motion we were looking for. And so magnesium is an interesting case in point, because if you start to dope magnesium with other metals, so in this case aluminum, you will get precipitation of intermetallic particles, but oftentimes the shape of them is not fortuitous for blocking dislocations. So you get these sorts of needle-like structures. But working with a colleague here, Tim Weiss, who's been doing equal angle axial extrusion, what he finds is that if he extrudes the material, heats it and pushes it through a right angle bend, then he can get it to precipitate the same kinds of intermetallic crystal structures, but as nanoscale particles. And these nanometer scale, nearly spherical particles are very useful for interfering with the dislocations in ways that strengthen the material. And so we'd like to understand, why do we get these nanoscale particles, and how can we develop processing methodologies that will reach that endpoint? And so this is the work of Vicente Munazaga, and what we've been exploring is the hypothesis that it's actually the formation of voids from vacancies that leads to the precipitation of these intermetallics. That basically magnesium, it's very difficult actually for the material to deform in particular directions. We know that that leads to the creation of vacancies, which are defects where atoms are absent in the lattice. If those vacancies are able to collect into small bubbles, essentially, those bubbles can be the places where the solute, the aluminum, collects within the magnesium, leading to the places that are fortuitous for intermetallic formation. So promoting the nucleation of the intermetallics and promoting it in a way that's dispersed within the material. So like all molecular dynamics simulations, any of a, molecular dynamics, as we said before, has a limitation in terms of its timescales. And but we can reach fairly long timescales if we use relatively simple potentials. So this uses an MEAM potential. I'll go into the details there. But the innovative thing about it is that it uses a technique called transition interface sampling to, rather than try to do a brute force simulation of the nucleation of the intermetallic particles, to actually statistically collect trajectories in the phase space that can be then sampled in order to derive the free energy of the transition. And so what that requires is defining a sort of progression parameter or order parameter that defines the transition from the initial state, which in our case would be dispersed vacancies throughout the material, and can track the progression of the material from that to the final state, that is the formation of one of these bubbles. And so one of the things that Vicente has been able to do is define such a progression parameter. Here, this has to do with the region in the material with the lowest local density. And he can measure that at a particular length scale. And then he can track in any given simulation how it transitions from dispersed vacancies to the formation of a bubble. Here we're looking at lambda as a function of time. And so this is just showing how the system changes as lambda is changing from the dispersed vacancies to a final void. And then that allows us to quantify the free energy as a function of the progression of the transition. And so we can then see how the free energy changes between, let's say, pure magnesium here in teal and the magnesium aluminum alloy in gray, and understand how the presence of the solute makes it fortuitous for the material to form the intermetallic particles. So, and with that, I'll just kind of wrap up by saying, I think the thing I wanted to deliver to you today is just the notion that computer simulation is itself a creative process. It involves thinking about how can I simplify the problem enough that I can get at the essential physics going on underneath in a way that's not cluttered with a lot of the details that the real system has, so that I have the potential to simulate it. And I think it provides a lot of insight in it. I think that that's has been a useful way for me to think about how to use computer simulation in my work. So I'll turn it over to you.
By the way, you will be using some of this adventures in the afternoon in the tutorial session. So you will be studying fraction. Okay, questions?
Okay. Yes.
One question I had, just out of curiosity, I'm not a material scientist. It's like what, like the shear and stress work that you were doing in the beginning, like showing the different points in the material that would rearrange the molecules. Like by gathering that kind of data, like how does that then like influence like how you can design materials in the future?
Right. So, I mean, like one of the questions, particularly in the metallic glass area, is let's say we had a metallic glass alloy and we could produce it, but now we want to ask, how does the way in which it was produced influence how strong or weak it is? If it had been cooled into the glass more quickly or more slowly, or if it had been alloyed at a slightly different composition, how would that change how strong it is? And so by understanding the micromechanisms, like how the local defects are influenced by the composition or by the way in which it was cooled, we can potentially influence the strength. And so, like one particular example that we're working on now is we would like to be able to come up with mechanisms whereby we could describe the additive manufacturing of a metallic glass part. So let's say you deposited the metal with laser onto a surface, and then be able to predict, oh, if we write it this way, this is where the weak spots are going to be. But if we write it that way, maybe the weak spots are going to be somewhere else. So I think having these kinds of insights allow us to potentially build predictive models of that
I want to see. I had a question about the, I guess like still the, how glass space, either a little spinning shear angle, application. Which remind me of how it was there. Do metallic glass exhibit any kind of like viscous response?
Oh, yes. I mean, that's one of the most important things about glassy materials is that unlike crystals that sort of stay in a relatively, solid state, there's very low viscosity, and then they undergo a discontinuous phase transition into a liquid, where clearly there's low viscosity. Glasses have a continuous transition from solid to liquid. So the viscosity increases over a relatively narrow temperature range. But it's that fact that you can sort of tune the viscosity with the temperature that makes them so formable. So when you think about somebody blowing glass, they can do that because they can heat the glass to a particular temperature at which they can control the viscosity to the point where, to be at exactly the point where they can blow it up like a balloon.
People do a little of that in the simulation by, for instance, changing your rate of shear.
Yeah, so definitely there are many people who look at how the viscosity is related to the temperature and the constituents of the glass in the computer. It's very, very beautiful, and it's basically very simple.
Yeah, so I'm also not a material scientist, so perhaps this went over my head a little bit, but the TIS sampling that you were talking about seems kind of similar to some work that I'm doing. So could you talk a little bit about the derivation of that order parameter, like any kind of physical significance, but more so why you feel it's an accurate metric to describe the transition from one configuration to another?
Yeah, actually, I mean, like many kinds of simulation, transition interface sampling is an art, right? In that you have to choose a progression parameter that's going to explain or define how you move the system from a particular configuration to another. But there are good choices and bad choices of order parameters. And there's a difficulty in sort of determining whether the progression parameter you've chosen. The reason why in the literature they use the term progression parameter is because they want to distinguish it from an order parameter. It's possible you choose a progression parameter that isn't an adequate order parameter. And so you have to sort of do the you have to choose someplace to start. So you propose a progression parameter, you do the statistical sampling, and then you check the statistical sampling to see if the progression parameter you chose is sufficient to be an order parameter. Or you might have to propose additional dimensions to describe how you're moving through phase space in order to find a more adequate order. Yeah.
Okay, any more questions? Let's thank Michael again. Now we are over time, so I'll be super fast and I'll wrap up this now in 5 minutes. So I want to end in spirit of this data-driven workshop. Think about how efficient our calculation in this laptop, calculation in our brain, it's going to design better intelligence, better information processing. So this is really designing intelligence of materials. And to illustrate the point, I'll go super fast. We're going to do a short experiment. Okay? Dan is here, he knows so. Don't spoil the fun. So we are going to compare this laptop. This laptop has a CPU that uses about 20 watts of power. Our brain is information processing soft material, it uses about 20 watts of power. Now we'll just evaluate what is the performance of our brain versus a laptop of the tasks, and then compare against that physical thermodynamic power. And see, in the future, in the next decades, where can we really improve? Okay, so I'll put an equation here, and I want you to solve in your head without using a computer. I will time you, okay? And when you've solved it, just raise your arm, okay? The faster you do it, the faster you get to eat lunch. Okay, ready, steady, go. What is this? Yeah,
15120.
that's 15120. Thank you. It took about 10 seconds. Okay. Now, how long would it take CPU or laptop to calculate this? You just do 50 times 42. 15120. And if we know a bit how computers work, well, the CPU can do this in one cycle, this gigahertz. So the CPU can do this in a nanosecond. Well, our brain, unless you're a genius, right? There are some geniuses out there that can do this maybe in a second. Our brain is about 10 seconds. Our brain is much worse at arithmetic. But now let's think of a different task. So I'm gonna pop an image up there. It's an image that you've never seen in your life. It's gonna be there for a fraction of a second. I mean, like 2/10 of a second. And I want you to tell me what's on the image. What do you see? Okay? Don't look at me, look at the screen. 3, 2, 1.
Child pushing a toy of some sort that vaguely looks like a lawnmower.
So child pushing a toy lawnmower. Anything else?
It's in a house.
The house, yeah, anything else?
The floors are wooden.
Sorry?
Floors are wooden.
Wooden floor, yeah, anything else?
There is red somewhere.
Yeah,
Color red at some point.
that's pretty good, that's pretty good. Now let's see how a computer does this. And I'm just gonna. So this is, I'm just gonna go to some image recognition online. If you just put image recognize in Google, that's what you get. Is it the best algorithm out there? Probably not, but it's also probably not the worst. So now let's give it this image, and this will run on my laptop. That's JavaScript.
So that was a lawnmower, right?
Yeah, you were right. That's thinking, right? It's thinking. In seconds. Okay.
Did is install the lawnmower and then extrapolated it would be outside.
Exactly. What's the problem? The problem with AI and signals. This AI ML was trained with images, and usually on the internet you only see lawnmowers and grass. Right? This happens to be a lawnmower that's toy lawnmower, it's not on grass. But because this image recognition algorithm is just trains lawnmowers are always on grass, it thinks that this is actually grass. Not. So we have grass, plant, lawn, wood, that's actually correct, right? Hardwood, boy, that's correct. Less confident about that. A child. That's correct. Person, correct. Floor, device, flooring, okay. E-scooter, well, nation, yeah. Here, yeah, it's kind of weird. So it did get some things right, but the main parts, I can totally. Why? Because well, this thing was trained on images where lawnmowers are always on grass. And it took a few seconds. Well, our brain did it in 2/10 of a second. So clearly, even though the power usage is similar between this CPU and our brain, the kind of things that they're good at is best to do. So. But now let's try to put some numbers on this, okay? What is now actually the efficiency if we compare to the fundamental physical bound? The fundamental physical bound was first investigated by Leo Szilard. Leo Szilard was working with Enrico Fermi. So the movie Oppenheimer, Leo Szilard was. Okay. So, and basically what this was done a long time ago, right? And Landau was working on this. And the important part is that information is physical. So if we want to obtain bit of information, to store it somewhere, that requires work. There's a fundamental physical boundary that says that if Landau's principle that this requires at least kb kilo. And you have to do with the entropy, because if we set a bit of memory, we have reduced the entropy of our system. Because before we had 0 1, now we know it's 1. If we reduce the entropy of our system, well, we have to, the entropy of the universe couldn't have decreased, so we have to use some work. Entropy also have to decrease. So this is our fundamental physical bound. Okay, so we cannot evaluate what is the efficiency of, let's say, a CPU of our brain relative to this bound. And that will tell us, well, how poorly we're actually doing. So I'll ask you, like, what do you think is the efficiency of the CPU of our brain? Really? Give me a number. What do you think? You all want to go for lunch, I'll just give you that. Okay. So basically, we can calculate this, and for multiplication, which is what the CPU actually does, the efficiency is actually good. That's my understanding. So there's a long way to go before we reach the fundamental physical bound. The efficiency of these things can increase way more. But our brain is much, much better. 10 to the minus 21. Terrible. It took about 10 seconds to calculate 20 watts of power to calculate single point. Now, if we do image recognition, then CPU does worse, our brain is a bit better. If we do a bit of a more complicated image like that, then our brain actually becomes better CPU. But the efficiencies are still super, super good. Then just an idea that we are nowhere near having good efficiency of our information processing system. There is a long way yet to go. It's something that we need to look at. And one important problem with this is that the power consumption of all this AI, ML, data centers is huge. It's projected to be like 20% of all the electricity generated. And I think a few days ago, I saw a news article that says that the US will not close its coal-powered power plants because of all the extra electricity demand from AI data centers. And that is because, well, the efficiency is just so low. Look at the image recognition efficiency of a CPU. Now, if you were to run this on a GPU, it would be 100 times better, but still be 10 to the minus 60. It's terrible. Absolutely terrible. But I'd like you to remember this. We want to design systems that are better than what we currently have. Because this CPU and the GPU that were designed to multiply numbers, and the GPU was designed to multiply vectors and vector operations that were not designed to run machine learning AI. We can do it, it's very efficient. And then we have some ideas how to do it with soft material today. We'll do this because we are getting for lunch. Just remember, there's a long way to go in designing material. we are extremely good at transforming work into heat, right? Efficiencies of internal combustion engines is close to 1, 10%, but information processing systems are 10 to the minus 10, 10 to the minus 20. So with that, I will close this. In the afternoon, we have tutorial session. Now we can go for lunch. Thank you. Any questions you can ask them during lunch? There we go for lunch.
Okay. Yeah.
Says, I can't still do.